The largest star ever found is not in our galaxy. It sits inside a smaller, wilder galaxy orbiting our own, hidden behind a curtain of dust so thick that for decades astronomers could not even look at it directly. When they finally managed to measure it, the number they calculated was so extreme that it pushed against the theoretical limits of what stars are supposed to be able to do. The star's radius is estimated at around 1,500 times that of our Sun. If it replaced our Sun at the center of our solar system, its outer atmosphere would reach past the orbit of Jupiter. Mercury, Venus, Earth, Mars, and every world we have ever known would be erased entirely, swallowed inside a single star. This is not a story about something exotic and remote. This is a story about the universe at its most extreme, about what happens when physics is pushed to the edge and matter concentrates itself into something so enormous that it defies the equations we built to describe it. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing, because what you're about to see only gets more surprising from here. Now, let's continue. Every star you can see in the night sky is a burning sphere of gas, held together by gravity and powered by nuclear fusion at its core. The Sun fuses roughly 600 million tons of hydrogen into helium every single second, releasing energy that keeps our planet warm and our atmosphere intact from 150 million kilometers away. The Sun is not a small object. Its diameter is about 1,400,000 kilometers. Its mass is so great that it accounts for 99.8% of everything in the solar system. And yet the star we are about to explore makes the Sun look like a single candle placed next to a city block of bonfires. To understand why a star like this exists, you first have to understand what makes stars grow in the first place. Stars are born from cold, dense clouds of gas and dust spread across galaxies. When one of these clouds becomes dense enough, gravity begins pulling it inward. As it collapses, it heats up, and a star ignites. The mass it ends up with depends on how much gas was available in the collapsing cloud, how fast the cloud was rotating, how turbulent the surrounding environment was, and crucially, what kinds of heavier elements were mixed into the gas. That last factor turns out to matter enormously. Astronomers use the word metallicity to describe the concentration of elements heavier than hydrogen and helium in a gas cloud. Confusingly, everything from carbon to uranium counts as a metal in this astronomical sense. These heavier elements are extremely efficient at radiating heat away. When a collapsing gas cloud contains a lot of them, it cools quickly and fragments into many smaller pieces, producing a large number of smaller stars. But when a gas cloud is poor in heavy elements, it stays warmer longer. It resists fragmentation. Instead of breaking into dozens of smaller stars, it can collapse into just a few enormous ones. This is why the most extreme stars in the modern universe tend to form in specific kinds of environments, galaxies that are chemically primitive, where the gas still carries the raw, unprocessed character of the early cosmos. The Large Magellanic Cloud is one such place. It orbits our Milky Way at a distance of roughly 163,000 light-years, a relatively close neighbor in cosmic terms. Despite being only about 1/10 the mass of the Milky Way, it punches far above its weight when it comes to producing massive stars. Its metallicity is lower than our galaxies, its star-forming regions are exceptionally turbulent, and the gravitational interaction between it and the Milky Way may be compressing and stirring its gas clouds, triggering bursts of intense star formation that the Milky Way itself rarely experiences. The most famous star-forming region in the Large Magellanic Cloud is the Tarantula Nebula, also known as 30 Doradus. It is one of the most active stellar nurseries in the entire local group of galaxies. Stars that would be impossibly rare in our galaxy are born there in clusters, dozens or even hundreds of massive objects forming nearly simultaneously in the same turbulent cloud. Some of these grow into ordinary massive stars. A few grow into something far beyond ordinary. The star known to astronomers as WOH G64 was first recorded in the 1970s by researchers Westerland, Olander, and Hedden, whose initials gave the star its designation. At the time, it was catalogued as an infrared source, a point in the sky that emitted more radiation in the infrared portion of the spectrum than you would expect from a normal star. This was already a clue that something unusual was happening. Stars that are surrounded by thick shells of dust emit much of their light at infrared wavelengths because the dust absorbs the shorter wavelength visible light and re-emits it at longer wavelengths. A strong infrared source often means a star that is shedding mass aggressively, wrapping itself in its own expelled material. Over the following decades, as telescopes improved and infrared observing techniques became more sophisticated, astronomers began to realize that WOHG-64 was not just an interesting infrared source. It was something genuinely extraordinary. In 2007, a detailed study using high-resolution interferometry at the Very Large Telescope in Chile confirmed what the data had been hinting at for years. The star had a radius estimated at around 1,500 times that of the Sun, and it was surrounded by a structure of dust that extended to about 1 light-year from its surface. That single number, 1,500 solar radii, placed it among the largest stellar objects ever measured. 1 light-year is the distance light travels in an entire year, approximately 9.5 trillion kilometers. The fact that a single star had produced enough expelled material to build a dust structure that large is not just remarkable in terms of scale. It is a statement about the star's violent internal state. Normal stars do lose mass over time. Our Sun sheds about 4.3 million tons of material per second through its solar wind, a stream of charged particles flowing outward from its surface. But the rate at which WOHG-64 appears to be losing mass is thousands of times higher than our Sun's, high enough that it has accumulated solar masses worth of material in its surrounding envelope. To get a concrete sense of what 1,500 solar radii actually means as a physical scale, consider this. The Sun's radius is about 696,000 kilometers. Multiply that by 1,500 and you get a radius of over 1 billion kilometers. A passenger aircraft traveling at around 900 kilometers per hour would need more than 75 years to complete a single orbit around the equator of this star. The same journey around our Sun would take about 6 months. Every unit of human experience we use to measure things breaks down when applied to an object like this. What makes this even more disorienting is that despite its enormous volume, WOHG-64 is not proportionally massive. Its mass is estimated at somewhere between 20 and 40 times that of the Sun. This disparity between volume and mass means the star's outer layers are extraordinarily diffuse. The density of the gas in its outer atmosphere is so low that it would constitute a near vacuum by the standards of most planetary atmospheres. A spacecraft could theoretically fly through the outermost regions of WOHG-64 and encounter less atmospheric resistance than it would entering Earth's upper atmosphere. The star is, in a sense, more like an extremely large cloud of plasma than a solid or even conventionally dense object. This diffuseness is not just a curiosity. It is central to understanding why the star behaves the way it does. Stars maintain their shape through hydrostatic equilibrium, a balance between two forces. Gravity pulls all the material inward toward the center. The pressure generated by nuclear fusion in the core pushes outward. When these forces are balanced, the star remains stable. But as a star grows older and runs through its fuel, that balance shifts. The core contracts and heats up. The outer layers expand dramatically in response. What was once a compact, dense object inflates into something vast, cool, and structurally fragile. This is the red giant and red supergiant phase of stellar evolution, and for the most massive stars it is both spectacular and brief. When a star like WOHG-64 entered this phase, it expanded outward with its outer layers growing increasingly diffuse, their grip on the star's gravity becoming weaker and weaker. At some point, the expansion crossed a critical theoretical boundary known as the Hayashi Limit, a line in the space of stellar parameters beyond which a star of a given mass cannot maintain stable hydrostatic equilibrium at low temperatures. According to standard models, a star that swells beyond this limit should either shed mass to bring itself back into balance or undergo structural instability. WOHG-64 appears to be doing both simultaneously. Its mass loss rate is among the highest ever documented for any star. The evidence is plain in the dust envelope that surrounds it. Astronomers have estimated that the material in that envelope corresponds to somewhere between 3 and 9 solar masses of expelled gas and dust. That means this star has already thrown off into space an amount of matter that exceeds the total mass of several stars like our Sun, and it is still doing so. The envelope continues to grow as the star bleeds itself into the surrounding interstellar medium. Interestingly, the dust envelope is not a uniform sphere. Observations with interferometric techniques have revealed that it has a toroidal structure, shaped something like a donut. This kind of geometry is not typical of a star that is simply puffing up evenly in all directions. It suggests that the mass loss is being channeled or sculpted by some additional force, possibly the star's own rotation, possibly magnetic fields in its atmosphere, or possibly the gravitational influence of an unseen companion star. The question of whether WOHG 64 is a binary system has been quietly debated among researchers for years. Most massive stars form in binary or multiple systems, and the extreme behavior of WOHG 64 is consistent with the kind of interactions that can occur when two massive stars orbit each other closely enough to exchange material or distort each other's outer layers. Some models suggest that a hot compact companion star, perhaps an O-type main sequence star, could be orbiting inside the dust envelope, accreting material from the red supergiant's wind and potentially reshaping the geometry of the outflow. No direct observation of such a companion has yet been confirmed. The dust is simply too thick and the system too distant to make definitive statements. But the toroidal structure of the envelope, the asymmetric features in spectroscopic data, and theoretical arguments about binary star formation all point in the same direction. If a companion exists, it would fundamentally change how we understand the star's evolution and how it will eventually die. Because WOHG 64 does not radiate primarily invisible light, most of what we know about it has been learned through infrared observations and spectroscopic analysis. The star's surface temperature is only around 3,000 to 3,400 Kelvin, which is cool enough to classify it as a red supergiant and means its peak emission is in the infrared. The surrounding dust absorbs much of even that infrared radiation and re-emits it at even longer wavelengths. Astronomers using instruments like the Spitzer Space Telescope and ground-based infrared spectrometers at the Very Large Telescope have been able to detect spectral signatures of silicon monoxide, carbon monoxide, water vapor, and complex silicate compounds in the star's atmosphere and surrounding material. These molecules tell a detailed story about the temperature, composition, and dynamics of the outflow. Spectroscopic velocity measurements reveal that the dust and gas are not flowing uniformly outward in all directions. Some spectral lines are shifted toward the blue end of the spectrum, indicating material moving toward us. Others are shifted toward the red end, indicating material moving away. These asymmetries suggest that the outflow occurs along preferred axes, consistent with the toroidal structure seen in imaging data. The internal convection of the star, its pulsations, and possibly interactions with a companion are all candidates for explaining why the mass loss is directionally biased rather than isotropic. The luminosity of WOHG 64, estimated at approximately 280,000 times that of our Sun, is equally staggering. Our Sun emits about 3.8 times 10 to the 26th watts of power. Multiply that by 280,000 and you begin to approach the scale of energy output that this star is sustaining every single second. The radiation pressure generated by that luminosity alone is a significant fraction of the force needed to blow the star's outer layers into space. This is one of the reasons massive stars lose mass at such high rates. Their light is literally pushing themselves apart. The theoretical framework for understanding this relationship between luminosity and mass loss involves a concept called the Eddington luminosity, which is the maximum luminosity a star can maintain before the outward force of radiation pressure equals the inward force of gravity. Stars that approach or exceed this limit cannot retain their outer layers indefinitely. They shed material until the luminosity drops back below the threshold. WOHG 64 is operating very close to this regime, and its extraordinary mass loss rate reflects the delicate and explosive tension between its luminosity and its ability to hold itself together. What we are observing when we study WOHG 64 is therefore not a stable star. It is a star in the process of actively dismantling itself. The outer layers are being pushed away by radiation pressure and stellar winds. The interior is burning through successively heavier nuclear fuels at an accelerating pace. In the core, hydrogen fusion gave way to helium fusion long ago. Helium fusion produces carbon and oxygen. Carbon fusion produces neon, magnesium, and sodium. Neon fusion produces oxygen, magnesium, and silicon. And silicon fusion, the final stage before catastrophic collapse, produces iron. The timing of these stages is one of the most dramatic escalations in all of stellar physics. Hydrogen fusion in the core of a massive star lasts millions of years. Helium fusion lasts hundreds of thousands of years. Carbon fusion lasts perhaps 1,000 years. Neon fusion lasts about 1 year. Oxygen fusion lasts months. Silicon fusion, the final stage, lasts only about 1 week before the core is dominated by iron, and iron cannot release energy through fusion. It absorbs energy. When the core becomes iron-rich, the power source is gone. The outward pressure from fusion ceases. Gravity, unchallenged, acts in milliseconds. The collapse of an iron core happens at roughly 1/4 the speed of light. In about a second, the core shrinks from a sphere hundreds of kilometers across to something the size of a city, roughly 20 kilometers in diameter. The density becomes so extreme that protons and electrons are forced together to form neutrons, and a neutron star is born, but the collapse does not stop cleanly. The infalling outer layers of the star strike the newly formed neutron star and rebound outward in a shock wave of staggering violence. Simultaneously, the neutron star releases an enormous flood of neutrinos, particles that interact only weakly with matter, but in quantities so vast that they deposit enough energy in the star's outer layers to help drive the explosion. The result is a core collapse supernova. For a star the size of WOH-G64, the energy released in such an explosion would temporarily outshine the entire Large Magellanic Cloud. For a period of weeks, a single dying star would pour out more light than billions of stars combined. The blast wave would propagate outward through the star's existing dust envelope at thousands of kilometers per second, compressing and heating the surrounding material, producing a cascade of electromagnetic radiation across every wavelength, from gamma rays and X-rays through ultraviolet and visible light down to infrared and radio waves. But whether this star produces a neutron star or a black hole at the end of this process depends on how much mass remains in the core when the collapse occurs. If the core mass at the time of collapse exceeds roughly 2 to 2.5 solar masses, neutron degeneracy pressure cannot halt the collapse. The neutron star itself is crushed. Gravity wins completely. Space-time curves without limit at a single point, and a black hole is born. Given the current mass estimates for WOH-G64 and the rate at which it is shedding material, astronomers consider it a strong candidate for direct collapse into a black hole, either through a supernova that leaves behind a black hole remnant, or through a failed supernova in which the star simply vanishes into a black hole without a spectacular explosion, which is itself a theoretically possible outcome for the most massive stellar collapses. The possibility of a hypernova is also on the table. Hypernovae are collapse events that are approximately 100 times more energetic than ordinary supernovae. They are associated with the formation of rapidly rotating black holes and with long-duration gamma-ray bursts, which are focused beams of extremely high-energy radiation launched in opposite directions from the collapsing core at near the speed of light. The total energy released in a gamma-ray burst event can equal the energy output of our Sun over 10 billion years, compressed into seconds and focused into a narrow beam. If such a beam were aimed at a planet orbiting a nearby star, the radiation dose would strip away the ozone layer and render the surface sterile in a matter of moments. Whether WOH-G64 could produce a gamma-ray burst remains uncertain. Most confirmed gamma-ray burst progenitors are stripped envelope stars that have lost their outer hydrogen layers before collapse, allowing the relativistic jet to punch through the remaining material and escape into space. WOH-G64 still retains a substantial hydrogen envelope, which could smother or deflect such a jet. But if the star is rotating rapidly enough and if its magnetic fields are sufficiently well aligned, there are models in which a jet could still escape. The conformation of a binary companion would also affect this calculation, since tidal interactions can spin up a star's rotation significantly. From Earth's perspective, WOH-G64 is safely located more than 160,000 light-years away. A gamma-ray burst from that distance, even aimed directly at us, would not carry enough energy to pose a planetary threat. But the observational opportunity such an event would present is immense. Telescopes sensitive to gamma rays, X-rays, ultraviolet, optical, infrared, and radio emission would all be pointed at the event simultaneously. The afterglow, which can persist for days, weeks, or months after the initial burst, would carry detailed information about the star's pre-explosion structure, the dynamics of the collapse, and the properties of the remnant. It would be one of the most comprehensively observed stellar death events in the history of astronomy. In the meantime, observational campaigns continue to monitor WOHG 64 across multiple wavelengths. Spectroscopic monitoring tracks changes in the star's brightness and spectral lines over time, looking for signs of increased instability that might signal an imminent change in the star's state. Interferometric imaging with instruments like the Very Large Telescope Interferometer attempts to resolve structural changes in the dust envelope and look for the subtle asymmetric motions that might indicate a binary companion. Radio telescopes listen for maser emission from molecules like silicon monoxide, which forms in the dense outflow close to the star's surface and can be used to probe the dynamics of the inner wind. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spatial resolution, represents a significant advance in our ability to study WOHG 64. Its ability to detect faint emission from within the dust cocoon may allow astronomers to get a cleaner measurement of the star's actual photospheric properties, separate from the reprocessed emission of the dust envelope. There is a realistic possibility that JWST observations will either confirm the current size estimates or revise them, potentially repositioning WOHG 64 in the ongoing contest to identify the physically largest stars known. That contest involves several remarkable objects. Betelgeuse, the famous red supergiant in the constellation Orion, has a radius of roughly 700 to 900 times that of the Sun, and is one of the most studied massive stars in the sky. Its irregular pulsations and famous dimming event in 2019 and 2020 demonstrated how dynamically complex these stars are. But Betelgeuse is not in the same category as WOHG 64 by size. Scuti, located roughly 9,500 light-years away in our own galaxy in the constellation Scutum, held the title of largest known star by radius for a number of years, with estimates placing it at up to around 1,700 solar radii. It is a pulsating red supergiant, meaning its size actually oscillates over time as internal pressure waves propagate through its enormous volume. This pulsation makes precise measurement challenging, since the star at its maximum extent is larger than at its minimum, and pinning down the exact outer boundary of a diffuse stellar atmosphere involves significant observational and theoretical uncertainty. Updated measurements have revised some earlier estimates of Scuti downward, but it remains one of the largest stars in the Milky Way. Stephenson 218, located roughly 19,000 light-years away in the constellation Scutum and embedded in the dense stellar cluster Stephenson 2, is another strong contender. It is one of the most luminous red supergiants known, with estimates suggesting a luminosity of at least 440,000 solar luminosities, possibly higher. Its size estimates have placed it at comparable or potentially larger dimensions than WOHG 64. But like many of these extreme objects, the measurements involve substantial uncertainty due to dust obscuration, distance ambiguity, and the inherent difficulty of resolving a diffuse atmosphere from this far away. Canis Majoris, another massive red supergiant at roughly 3,900 light-years, was once the record holder before subsequent observations revised its estimated radius downward. Mutsepe, sometimes called the Garnet Star for its distinctly red color, is one of the most visually striking massive stars in our galaxy, with a radius estimated at around 1,260 solar radii and a luminosity approximately 350,000 times that of the Sun. What all of these objects share is their location on the extreme upper right of the Hertzsprung-Russell diagram, the plot of stellar luminosity against surface temperature that serves as the fundamental map of stellar evolution. Red supergiants occupy a region of this diagram where theory predicts stars should barely be able to exist in stable configurations. The Hayashi limit is one boundary. The Humphreys-Davidson limit is another, an empirically observed upper boundary in luminosity for cool massive stars, above which no stars are found. The most extreme red supergiants sit right at or near these boundaries, implying that they are objects in the most marginal state of stability, constantly teetering on the edge of structural failure. For WOHG64, the situation is even more extreme. Its estimated position on the diagram places it at, or potentially beyond, the Hayashi limit for its mass, in a region where no star should be able to maintain hydrostatic equilibrium. The fact that it exists there, however briefly on cosmic timescales, suggests that the standard theoretical boundaries need refinement. Either the models are missing physical mechanisms that stabilize these stars temporarily, or the star is already in a state of irreversible structural collapse that is occurring slowly enough to be visible as a relatively static configuration, even though the end is near. One candidate mechanism is the role of the circumstellar dust envelope itself. If the mass loss from the star is rapid enough that the outflowing material carries away angular momentum and energy, it could be providing a kind of pressure valve that prevents the star from collapsing faster. The star is simultaneously losing mass through its surface, which reduces the pressure the outer layers exert on the core, and the reduction in surface gravity as the outer layers thin out means that the remaining material has an easier time escaping. This creates a feedback loop in which mass loss sustains the extended structure of the star even past the point where it should be stable. Another possibility involves internal convective mixing. Massive red supergiants experience powerful convective cells in their outer envelopes, analogous to, but far larger than the convective cells on the Sun's surface, which give it its granular texture when viewed in detail. For a star the size of WOHG64, these convective structures could be enormous, potentially as large as the entire Sun. The mixing they produce distributes energy through the stellar envelope in ways that could extend the star's stability beyond what simple spherically symmetric models predict. The question of how and when WOHG64 will actually die is therefore tied up in these unresolved physical questions. The star is already losing mass at a rate that, if sustained, would result in the ejection of most of its envelope within a cosmically short time. Some models suggest that the star may transition out of the red supergiant phase entirely before it collapses, moving to hotter temperatures as the outer hydrogen envelope is stripped away, potentially becoming a yellow or blue supergiant, or even a Wolf-Rayet star with a bare, exposed core. This kind of evolutionary track has been observed in other massive stars. The star Sandelique -69°202, which was the progenitor of supernova 1987A in the Large Magellanic Cloud, was a blue supergiant at the time of its explosion, suggesting it had evolved from a red supergiant phase back toward hotter temperatures before its final collapse. Supernova 1987A is itself one of the most instructive cases in modern stellar astrophysics. It was the first naked-eye supernova visible from Earth since 1684, and its proximity in the Large Magellanic Cloud, at about 168,000 light-years, allowed astronomers to study it in unprecedented detail across essentially every wavelength of the electromagnetic spectrum. Neutrinos from the explosion were detected by underground neutrino detectors on Earth, providing the first direct observational confirmation of the theoretical prediction that a collapsing stellar core produces a flood of neutrinos. The expanding debris cloud from that explosion has been monitored continuously ever since, providing a real-time laboratory for studying how supernova remnants evolve. The remnant of WOHG64, should it explode during or after the era of modern large-aperture telescopes, would be similarly transformative for the field. Given the star's location in the Large Magellanic Cloud, it would be close enough to study in exceptional spatial detail, with instruments like the extremely large telescope currently under construction in Chile, which will have a primary mirror 39 meters in diameter, or with space-based successors to the James Webb Space Telescope. The chemical signatures of the explosion, the dynamics of the expanding shockwave, the behavior of the remnant neutron star or black hole, and the interaction of the blast with the pre-existing dust envelope would all be observable in a way that simply cannot be achieved for supernovae in more distant galaxies. One particularly interesting aspect of the WOHG64 system is what it tells us about dust production in galaxies. Dust is not merely an astronomical nuisance that obscures observations. It is a fundamental ingredient in the chemistry of galaxies and in the formation of planets. Dust grains provide surfaces on which molecules can form. They are incorporated into the solid bodies of planetary systems, and they absorb starlight and re-emitted at infrared wavelengths in a way that significantly affects the energy balance of galaxies. The sources of cosmic dust are a matter of ongoing research. Asymptotic giant branch stars, which are intermediate mass stars in the final stages before they shed their envelopes as planetary nebulae, are known to be significant dust producers. Supernovae are also dust producers, though observations of how much dust survives the reverse shock of a supernova explosion are still being refined. Massive red supergiants, like WOHG 64, are increasingly recognized as potentially major contributors to the dust budget of their host galaxies, particularly in environments where the stars are forming and dying rapidly. The amount of dust in WOHG 64's circumstellar envelope, estimated at several solar masses worth of material, suggests that when this star finally explodes, it will seed a significant volume of the surrounding interstellar medium with dust grains and heavy elements, potentially triggering a new round of star formation in the compressed gas swept up by the blast wave. The material ejected in this way carries all the elements synthesized during the star's lifetime, from helium and carbon to oxygen and silicon, as well as the heavier elements produced in the final moments of the explosion itself. This nucleosynthesis is the process by which stars are the true manufacturers of chemical complexity in the universe. The early universe, formed in the Big Bang roughly 13.8 billion years ago, contained almost nothing except hydrogen and helium, with trace amounts of lithium and beryllium. Every other element in the periodic table was produced inside stars and dispersed into the interstellar medium through stellar winds and supernova explosions. The carbon in organic molecules, the oxygen dissolved in oceans, the iron at the cores of rocky planets, the calcium in bone, the gold in jewelry, the uranium in nuclear reactors, all of it was forged in stellar interiors and scattered by stellar deaths. Massive stars are the primary factories for the heavy elements, the ones beyond iron, which can only be produced in the extreme conditions of a supernova explosion or a neutron star merger. In this sense, stars like WOHG 64 are not distant curiosities. They are directly relevant to the existence of chemistry, geology, biology, and everything we consider complex in the physical world. The atoms currently making up the stellar envelope being shed into the Large Magellanic Cloud will eventually mix into the interstellar medium, cool and condense into new molecular clouds. Those clouds will collapse to form new stars and planetary systems. Some of those systems will have the chemical richness to support rocky planets with complex geochemistry, and on some subset of those planets, under the right conditions, chemical complexity might give rise to biological complexity. The chain of causation connecting the death of a massive star to the eventual emergence of life is not metaphorical. It is literal and physical. Studying WOHG 64 therefore connects to one of the deepest questions in science. Why does the universe contain anything other than hydrogen and helium? The answer runs through stars, and the stars that have contributed most to building chemical complexity are the most massive ones, the ones that burn fastest and die most violently, the ones that produce the largest variety of heavy elements and distribute them most widely through their environments. WOHG 64 is among the most massive stars we have ever found, and understanding it in detail means understanding one of the most significant engines of cosmic chemical evolution. The comparison between WOHG 64 and other extreme stars also reveals how difficult it is to pin down the properties of these objects with certainty. The ranking of the largest known stars has shifted repeatedly over the decades as observational techniques improved and new measurements were applied. Stars that were once considered record holders have been revised downward. New candidates have emerged as infrared surveys, and interferometric techniques have penetrated dust-obscured regions of nearby galaxies. The lesson is that our knowledge is provisional and evolving. The star we currently believe to be the largest will likely be either revised or superseded as new data comes in. This is not a failure of astronomy. It is a reflection of how genuinely difficult it is to measure a diffuse, dust-enshrouded stellar atmosphere at a distance of tens of thousands of light years. The physical boundary of a red supergiant's atmosphere is not a sharp edge like the surface of a planet. It is a gradual transition from dense plasma to thin stellar wind, and where exactly you draw the line depends on what wavelength you observe at and what physical definition of radius you apply. Different observational techniques and different theoretical models can give different answers. The most careful current estimates for WOHG 64 place its radius somewhere in the range of 1,200 to 1,500 solar radii, which already represents a range of 300 solar radii in uncertainty, a range that is itself several hundred times the radius of Earth. The existence of stars, this extreme forces astronomers to confront the limits of standard stellar evolution models. These models were developed primarily for stars in the mass range up to a few tens of solar masses, and while they have been extended to higher masses, the behavior of stars in the most extreme part of the parameter space, where WOHG 64 lives, is poorly constrained by observations and involves physical processes, including three-dimensional convection, radiation hydrodynamics, and pulsational instabilities that are extremely challenging to simulate accurately. New generations of computational models are beginning to address these challenges. Three-dimensional radiation hydrodynamic simulations of red supergiant convection have revealed that the convective structures in these stars can be dramatically larger and more irregular than classical one-dimensional models assumed. These large-scale convective plumes can carry significant amounts of material to the stellar surface, launching it into the wind in episodic bursts rather than a steady flow. This episodic nature of the mass loss may explain why the dust envelopes of extreme stars like WOHG 64 have such complex, asymmetric structures. The detection of stellar oscillations in red supergiants also provides an independent probe of their internal structure. Just as seismology on Earth uses seismic waves to map the interior of the planet, astroseismology uses the surface manifestations of internal waves in stars to constrain their density profiles, chemical compositions, and evolutionary states. WOHG 64's dense dust envelope makes direct optical monitoring of its brightness variations challenging, but radio interferometry of its maser emission can track motions in the inner wind on timescales of months to years, providing indirect information about the star's pulsation behavior. Future observations at radio wavelengths with instruments like the Atacama Large Millimeter Array may reveal the three-dimensional structure of the molecular outflow in enough detail to constrain the star's pulsation period and track changes in the mass loss rate over time. Combined with infrared monitoring from space, this kind of multi-wavelength campaign would provide a comprehensive picture of the star's physical state and how it is evolving. If the James Webb Space Telescope can penetrate the dust envelope well enough to detect the photospheric emission directly, it would also allow a much more accurate determination of the stellar radius and temperature, potentially resolving some of the current uncertainty in the size estimates. One of the broader contexts in which WOHG 64 sits is the question of how massive stars at the extreme end of the mass spectrum behave, differently from their less extreme cousins. The upper mass limit for stars, sometimes called the stellar mass limit, is thought to be around 150 to 300 solar masses, based on theoretical arguments about the instability that develops in the cores of very massive stars, where radiation pressure becomes so dominant that any perturbation can trigger runaway expansion or collapse. Stars close to this limit are called very massive stars, or supermassive stars, and they evolve along trajectories that are quite distinct from those of more ordinary massive stars. HG64, with a mass of perhaps 20 to 40 solar masses, is not in this extreme category in terms of mass, but it is extreme in terms of physical size and mass loss rate. This combination places it in a poorly explored region of parameter space where the interplay between stellar evolution, mass loss, and circumstellar environment produces behavior that standard models struggle to reproduce. Understanding how such stars behave, how long they survive in this extreme state, what triggers their final collapse, and what kind of remnant they leave behind, requires dedicated observational campaigns and targeted theoretical work that is now underway in stellar physics research groups around the world. The implications extend beyond individual stellar systems. If stars like WOHG 64 are more common than previously thought, or if their mass loss rates are higher than models assumed, then they could be playing a larger role in the chemical enrichment of their host galaxies than current models account for. In the Large Magellanic Cloud, With its relatively low metallicity and high star formation rate, extreme red supergiants could be significant sources of heavy elements and dust, enriching the interstellar medium in ways that affect subsequent generations of star and planet formation throughout the galaxy. There is also a connection to the study of the early universe. The conditions in the Large Magellanic Cloud, with its low metallicity and chaotic star-forming environment, resemble in some ways the conditions in galaxies in the early universe, when heavy element enrichment had not yet proceeded as far as it has in our own galaxy today. Stars formed in low metallicity environments tend to be more massive on average and to evolve differently from stars formed in metal-rich environments. By studying extreme stars in the Large Magellanic Cloud, astronomers can gain insight into how the first generations of massive stars in the early universe behaved, how they enriched their surroundings, and how they set the stage for the complex chemical evolution that eventually made the formation of rocky planets and complex chemistry possible. The observation that the universe we inhabit, with its rich chemistry and its potential for biology, was made possible by the deaths of massive stars like WOHG 64, is one of the most profound insights that astrophysics has produced. The iron in Earth's core, the oxygen in the atmosphere, the calcium in biological structures, none of it was produced in the Big Bang. All of it was forged in stellar interiors and scattered by stellar explosions over billions of years before our own sun and solar system formed from the enriched debris. We are, in a very literal chemical sense, composed of star stuff, and the stars that contributed most to producing that chemical richness were the most massive ones, the ones that burned fastest and exploded most violently. WOHG 64 has not yet exploded. It is still burning, still shedding its outer layers into the surrounding interstellar medium of the Large Magellanic Cloud, still defying the theoretical boundaries that say a star this large and luminous should not be able to maintain its current configuration. It has been doing this for millions of years. It may continue for tens of thousands more, or it may collapse tomorrow on cosmic timescales. The light we observe from it today is light that left the star before modern humans existed, before agriculture, before recorded history, before our species had even fully developed. What the star looks like right now at this moment, we cannot know. We are seeing a delayed image, a snapshot from a past that is 163,000 years removed from our present. This temporal displacement is one of the stranger aspects of astronomical observation. When we point a telescope at WOHG 64 and measure its spectrum and its brightness and the structure of its dust envelope, we are not seeing the star as it is. We are seeing the star as it was when our ancestors were living in small groups on the plains of Africa. The explosion, if it has already occurred, is 163,000 light-years away from reaching us. The photons that will announce the death of this star, the sudden brightening in the sky, the flood of neutrinos that will travel through the Earth, the burst of gravitational waves if the remnant forms a compact object. All of these signals are already traveling toward us. Or they are not, depending on whether the star has yet died. We will not know until the signals arrive. When they do arrive, the astronomical community will mobilize rapidly. The detection of neutrinos from supernova 1987A came just hours after the optical brightening was first noticed, and it was the first direct detection of neutrinos from a cosmic source other than the Sun. A similar event from WOHG 64 would trigger simultaneous observation campaigns across every wavelength of the electromagnetic spectrum, from radio telescopes measuring the master emission from the expanding outflow, to gamma-ray observatories searching for the signature of a gamma-ray burst, to gravitational wave detectors listening for the vibrations of a collapsing stellar core. The breadth and depth of information that could be extracted from such an event would transform our understanding of stellar death and its aftermath. For now, we wait and watch. The instruments become more sensitive. The models become more sophisticated. New telescopes go online with capabilities their predecessors could not match. And WOHG 64 continues its slow, violent dissolution, shedding solar masses of material into the Large Magellanic Cloud, defying the equations, maintaining its impossible configuration for another year, another century, another millennium. It is a star that should not be, and yet it is. That tension between what theory predicts and what observation reveals is the engine of scientific progress, the signal that something important is not yet understood. The biggest stars are not just objects of wonder. They are tests of our best theories, challenges to our current understanding, and windows into the processes that made the universe chemically complex enough to harbor life. Every time we look at WOHG 64 and try to explain what we see, we are also explaining something about where we came from. The atoms that compose everything around us passed through stellar interiors before they found their way into the molecular cloud that collapsed to form our solar system. The energy that powers our civilization is ultimately derived from a sun that was itself formed from the ashes of stars that came before. The chain of creation runs from the first stars through generations of massive, short-lived giants to the moderate sun we orbit today. Understanding the most extreme end of that chain, the stars like WOHG 64 that pushed every limit and eventually exploded with enough violence to reshape their galactic neighborhoods, is essential to understanding how the universe became what it is. These are not peripheral curiosities at the extreme fringes of stellar physics. They are central actors in the story of cosmic evolution. Their lives and deaths have shaped the composition of galaxies, the formation of planetary systems, and ultimately, the conditions that made chemistry complex enough to produce organisms capable of looking back up at the sky and asking where all of this came from. We are still asking that question. The tools are getting better. The models are getting more sophisticated. The observations are becoming more detailed. And the answers, when they come, will be found in the light of stars like WOHG 64, the biggest star ever found. A bloated and violent giant burning its last fuel in a small wild galaxy orbiting our own, shedding itself into the cosmos one solar mass at a time, waiting, unknowingly, for the iron to accumulate and gravity to have the final word. If this exploration of the universe's most extreme stellar object intrigued you, if the scale of what is possible in the cosmos left you wanting to understand more, consider sharing this with someone who looks up at stars and wonders what they really are. There's always more to discover at the edge of what we know. Red supergiants as a class occupy one of the most dramatic chapters in the story of stellar evolution. To appreciate what WOHG 64 represents at the extreme end of this class, it helps to understand how even ordinary red supergiants compare to everything else in the universe. When our sun eventually exhausts the hydrogen in its core, roughly 5 billion years from now, it will begin to swell into a red giant. Its outer layers will expand outward as the core contracts and heats up, pushing the photosphere out to roughly 200 times its current radius. This transformation will almost certainly engulf the inner planets. Earth, if it survives at all, will be rendered uninhabitable long before the sun's surface reaches it, as the increased luminosity will evaporate our oceans and strip our atmosphere. And this is a completely ordinary stellar death, the fate of a star of entirely average mass and size. Now consider Betelgeuse, the red supergiant familiar to most people as the orange-red star marking the right shoulder of the constellation Orion. Betelgeuse has a mass roughly 15 to 20 times that of our Sun, and at its current swollen state, its radius is estimated at around 700 times solar. If Betelgeuse replaced our Sun, its surface would extend to roughly the orbit of Mars. The star is so large that it was the first stellar surface ever resolved into a disk shape by very long baseline interferometry, allowing astronomers to actually see that its surface is not uniform but modeled with large convective structures, bright and dark regions produced by the enormous circulation cells carrying hot plasma from its interior to the surface. Betelgeuse has also demonstrated how dynamically active red supergiants can be. In late 2019 and early 2020, the star underwent what became known as the Great Dimming, a period of unprecedented fading that reduced its brightness by roughly a factor of 3 and sparked widespread speculation about whether a supernova was imminent. Subsequent analysis revealed that the dimming was caused by the ejection of a large mass of cool gas and dust from the stellar surface that blocked the star's light as it expanded outward. This was a dramatic demonstration of how episodic and powerful the mass loss from red supergiants can be. Even for a star far less extreme than WOHG 64, the Betelgeuse Great Dimming also highlighted how much we still do not understand about these stars. Even with decades of careful observation and sophisticated models, the dimming event was not predicted. It resulted from a complex interplay of stellar pulsations, convective eruptions, and atmospheric cooling that standard models did not capture quantitatively. If this is true for Betelgeuse, which is one of the most intensely studied stars in the sky precisely because of its brightness and proximity, then our ignorance about the behavior of more extreme and more distant objects like WOHG 64 is proportionally greater. The question of stellar pulsations in red supergiants is particularly important. These stars oscillate in size and brightness on timescales ranging from months to years, driven by complex interplay between convection, radiation pressure, and the pulsation modes of the stellar envelope. For some red supergiants, these pulsations are remarkably regular, suggesting a dominant pulsation period that reflects the star's mean density and internal structure. For others, including WOHG 64, the variability is irregular and complex, possibly reflecting multiple overlapping pulsation modes or the episodic nature of the mass loss. The pulsations of a red supergiant are not merely aesthetic. They are physically important because they can drive mass loss. As the star expands in a pulsation cycle, the surface gravity decreases and the outer layers become easier for radiation pressure to lift off the star entirely. When the pulsation reaches its maximum extent, the atmosphere is more tenuous, more extended, and more vulnerable to being swept away by the stellar wind. This creates a mechanism by which the pulsation energy is converted into kinetic energy of the outflowing material, effectively pumping mass into the circumstellar envelope with each oscillation. For a star as extreme as WOHG 64, this pulsation-driven mass loss mechanism may be operating at maximum efficiency, contributing to the star's extraordinary mass loss rate. The circumstellar envelope of WOHG 64 is itself a scientifically rich object. The chemistry of the dust and molecules in this envelope reflects the nucleosynthesis that has occurred in the star's interior over its lifetime. The silicon monoxide and carbon monoxide detected in spectroscopic observations form in the dense inner wind close to the stellar surface. Silicate dust grains condense further out where the temperature has dropped enough for them to be stable. Even further out, more complex molecular species can form as the density decreases and the radiation field becomes less intense. The spatial distribution of these different molecular and dust species traces the thermal and density structure of the outflow, providing information about the history of the star's mass loss and the conditions in its atmosphere. Radio. Observations of the silicon monoxide maser emission from the inner wind of WOHG 64 have been particularly informative. Masers are the radio equivalent of lasers, sources of amplified stimulated emission at specific frequencies. In a red supergiant wind, certain transitions of silicon monoxide molecules can be inverted in population, meaning more molecules are in an excited state than in the ground state. When radio photons at the maser frequency pass through this inverted medium, they stimulate additional emission rather than absorption, producing an amplified signal that can be many times brighter than thermal emission at the same frequency. The positions and velocities of these masers map the inner wind in 3 dimensions, showing how material flows away from the stellar surface and how the flow varies with direction and time. The toroidal structure of the dust envelope, revealed by infrared interferometry, provides a complementary picture on larger scales. The fact that the dust is preferentially distributed in a disk-like structure rather than a sphere suggests that the mass loss is anisotropic, more intense in some directions than others. This could be driven by the star's rotation, with the equatorial regions experiencing stronger centrifugal effects that reduce the effective surface gravity and allow material to escape more easily. It could also reflect the influence of a binary companion whose orbital motion and gravitational pull could shape the outflow into a spiral or disk-like pattern. Both mechanisms have theoretical support, and distinguishing between them requires the kind of high spatial resolution observations that only interferometry at radio and infrared wavelengths can provide. The role of magnetic fields in the behavior of red supergiants is another area of active research. Magnetic fields can affect the structure of stellar atmospheres, contribute to angular momentum loss through magnetized winds, and potentially trigger or modulate mass ejection events. In the Sun, the magnetic field is generated by a dynamo mechanism in the convective zone, and its behavior is responsible for phenomena ranging from sunspots to solar flares to coronal mass ejections. In red supergiants, the deeper and more vigorous convection, combined with potentially slower rotation, may generate very different magnetic field configurations. Observations of polarized light from red supergiants provide some constraints on their magnetic fields, but the field strengths and geometries are still poorly known. For WOHG64, the potential presence of a binary companion adds another layer of complexity. Binary star systems can generate strong tidal effects that distort and synchronize the rotation of the component stars. If WOHG64 is in a sufficiently close binary orbit, tidal forces from the companion could be influencing the star's rotation rate, its internal angular momentum distribution, and consequently its magnetic field and mass loss patterns. The toroidal dust structure might even be a direct manifestation of these tidal interactions, with the companion's gravity sculpting the outflow into a preferential direction. The broader class of second fraction are close enough that mass transfer, tidal interactions, or eventual merger will dramatically alter the evolutionary history of one or both stars. The most extreme outcomes, where a neutron star or black hole accretes from a companion star, produce phenomena including X-ray binaries, millisecond pulsars, and eventually the compact binary mergers that produce gravitational waves detectable by instruments like LIGO and Virgo. In this context, WOHG64 may not be a single isolated stellar oddity, but rather a representative of a broader population of massive stars in late evolutionary stages whose behavior is significantly influenced by their binary status. If future observations confirm the presence of a companion, it will open up an entire new dimension of analysis, including the measurement of the orbital period, the mass ratio, the rate of mass transfer, and the eventual fate of the system as the red supergiant dies and leaves behind a compact remnant. The death of a binary system in which one component is a massive red supergiant can produce several distinct outcomes. Depending on the masses and orbital separation of the components, if the red supergiant explodes as a supernova, the explosion ejects most of the star's envelope at high velocity. This ejecta passes over the companion star, stripping away some of its outer layers and delivering a significant momentum kick. The sudden loss of mass from the system can also disrupt the orbit, potentially unbinding the system entirely and sending both stars, or what remains of them, flying apart in different directions. Alternatively, if the supernova remnant is a neutron star and the binary remains bound, the system can evolve into a high-mass X-ray binary in which the neutron star accretes material from the companion's stellar wind, emitting X-rays that betray its presence to our telescopes. Eventually, if the companion also evolves to explode as a supernova, the system can produce a bound pair of neutron stars, known as a double neutron star or binary pulsar. These systems are extraordinarily stable and precise, with the two neutron stars orbiting each other while emitting radio pulses with a regularity that rivals the best atomic clocks. By measuring the rate at which the orbital period decreases due to gravitational wave emission, astronomers can precisely test the predictions of general relativity. This was first achieved by Hulse and Taylor in their study of the binary pulsar PSR B1913+16, a discovery that led to the Nobel Prize in Physics in 1993. The connection from a red supergiant like WOHG64 through its eventual death to a neutron star or black hole, and possibly to a compact binary system that eventually merges and produces gravitational waves, represents the full arc of massive stellar evolution and its consequences for the broader cosmos. Gravitational wave detectors like LIGO, Virgo, and the planned future detector LISA are already revealing the population of compact binary mergers in the nearby universe, tracing the statistics of these events back to the massive star populations from which they originated. In this way, the study of a single extreme red supergiant in the Large Magellanic Cloud is connected to the cutting edge of gravitational wave astronomy. The Large Magellanic Cloud itself plays a special role in these connections because it is close enough to observe individual stars in detail but far enough to contain a statistically representative sample of stellar objects. It serves as a benchmark for theories of stellar evolution and stellar populations. The Milky Way contains too much dust in its plane for us to census its stellar population comprehensively. External galaxies beyond the local group are too distant for individual stellar observations. The Large Magellanic Cloud hits a sweet spot, where detailed stellar physics can be connected to broader, galactic scale properties. This made the Large Magellanic Cloud the ideal site for a transformative event in stellar astrophysics. On the 23rd of February 1987, supernova 1987A exploded in the Large Magellanic Cloud at a distance of about 168,000 light-years. It was the closest supernova to Earth since Kepler's supernova in 1604 and the first visible to the naked eye in the modern era of astronomy. Within hours of the optical discovery, neutrino detectors in Japan, the United States, and the Soviet Union recorded bursts of neutrinos arriving just before the optical brightening, confirming the theoretical prediction that a core collapse supernova should produce a flood of neutrinos in the instant of collapse. The progenitor star, Sanduleak -69°202, had been catalogued years before the explosion and turned out to be a blue supergiant, which was unexpected since the standard theory at the time predicted that core collapse supernovae should come from red.
Supergiants. This discovery forced a
revision of stellar evolution models for massive stars in low metallicity. Environments like the Large Magellanic Cloud, where it is now understood that the evolutionary tracks can differ significantly from those in metal-rich galaxies like the Milky Way. Stars that would remain as red supergiants in a metal-rich environment can evolve back to hotter, more compact configurations in low metallicity environments because the reduced opacity of metal-poor stellar material allows the star to radiate more efficiently. This makes the eventual supernova more likely to come from a blue or yellow supergiant rather than the conventional red variety. For WOHG-64, this has implications for how it might die. If it loses enough of its hydrogen envelope through its current intense mass loss or through interaction with a binary companion, it could evolve away from its current red supergiant configuration to a hotter and more compact state before its eventual core collapse. In that case, the supernova could resemble supernova 1987A in some ways, with a compact blue progenitor and the same general core collapse mechanism, but potentially with different dynamics in the explosion and a different kind of circumstellar interaction as the blast wave hits the complex dust structure that the star has already built around itself. The circumstellar interaction between a supernova blast wave and the pre-existing stellar wind material is itself a scientifically rich phenomenon. When the fast-moving ejecta from the explosion collides with the slower-moving circumstellar material, it produces a shock wave that heats the material to temperatures of millions of degrees, generating bright X-ray emission. Radio emission is also produced as electrons are accelerated by the shock and emit synchrotron radiation. The light curve of the X-ray and radio emission from this interaction carries detailed information about the density structure of the circumstellar medium, which reflects the history of the progenitor, star's mass loss in the years and centuries before the explosion. For a star like WOHG-64 that has been shedding mass at an extraordinary rate for an extended period, the circumstellar interaction could be particularly dramatic. The dense dust envelope surrounding the star would be swept up and heated by the expanding shock wave, producing a bright infrared and optical signal that could last for years or decades after the initial explosion. This kind of interaction supernova, where the ejecta is visibly interacting with dense circumstellar material, has been observed in several objects catalogued as supernova events in nearby galaxies. Some of these, like supernova 2006 GI, were so luminous that they exceeded the standard supernova luminosity by a factor of hundreds, qualifying as superluminous supernovae in which the extra energy comes from the kinetic energy deposited in the dense circumstellar medium rather than from the radioactive decay of nickel produced in the explosion. Whether WOHG-64 would produce a similarly superluminous event depends on how dense and how close in the circumstellar material is at the time of the explosion. If the mass loss rate remains as high as it currently appears to be, and if the outflow velocity is relatively slow, as expected for a red supergiant wind, the circumstellar density could be high enough to power a very luminous shock interaction. On the other hand, if the star loses most of its envelope before collapsing and the wind becomes faster and less dense in the final phase, the circumstellar interaction would be less energetic. The uncertainty reflects our incomplete knowledge of how the mass loss rate evolves in the final stages before a massive star's death. These final stages, the last 1,000 years, the last century, the last decade of a massive star's life, are among the least understood chapters in stellar astrophysics. The reason is partly statistical, since these phases are too brief for us to expect to catch many stars in this state, and partly observational, since the signatures of the final evolutionary stages are often obscured by dust. Direct imaging of the region around a massive star in the years before its explosion, followed by imaging after the explosion, can reveal the circumstellar environment that the progenitor had built up. The advent of systematic sky surveys that monitor the brightness of millions of stars in nearby galaxies has made it possible to identify the progenitors of supernovae by looking up their pre-explosion images in archival data. This has confirmed that most core collapse supernovae come from red supergiants, exactly as expected, but has also revealed some surprises, including cases where the progenitor appears to have brightened dramatically in the years before the explosion, possibly indicating a final burst of mass loss. HG64 has already demonstrated unusual behavior in terms of its mass loss and circumstellar environment. Long-term monitoring of its infrared brightness and spectral properties would be enormously valuable for understanding how this behavior evolves over time and whether any changes signal an approach to the final phase. Such monitoring campaigns are possible with existing telescope facilities and represent a relatively modest investment of observing time compared to the scientific returns that could be obtained from catching a star like this in its final evolutionary phases. The broader context of massive star monitoring programs in the Large Magellanic Cloud and other nearby galaxies has expanded enormously in recent years as dedicated survey telescopes have come online. The Zwicky Transient Facility, the all-sky automated survey for supernovae, and other wide-field photometric surveys continuously monitor millions of galaxies for signs of new supernovae and stellar transients. When a supernova is detected, alert systems notify astronomers within hours, triggering rapid follow-up observations across every available wavelength. In the era of these large-scale transient surveys, the chance of detecting a supernova in a nearby galaxy like the Large Magellanic Cloud and following it comprehensively from the first hours of its explosion is higher than at any previous point in history. The coming decade will also see the Virasi-Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, begin operations in Chile. This instrument will repeatedly scan the entire southern sky every few nights to a depth far greater than any previous survey, producing an enormous dataset of stellar and galactic variability. Its monitoring of the Large Magellanic Cloud will be particularly comprehensive, detecting brightness changes in individual stars with unprecedented sensitivity. If WOHG64 undergoes any significant brightening, dimming, or variability on timescales of days to years, the Rubin Observatory will detect it, potentially providing early warning of changes in the star's internal state. At the same time, advancements in theoretical modeling are beginning to close some of the gaps in our understanding of how extreme massive stars behave. Three-dimensional magnetohydrodynamic simulations of stellar convection, while computationally demanding, are revealing details of how convective plumes interact with stellar magnetic fields and how this interaction affects the structure and dynamics of the outer stellar envelope. Radiation hydrodynamics. Simulations of stellar winds are improving in their treatment of dust formation and growth in the circumstellar environment, producing more accurate predictions of mass loss rates and circumstellar structures that can be compared directly with observations. Machine learning techniques applied to large photometric and spectroscopic datasets are identifying new correlations and patterns in the behavior of variable massive stars that may reveal previously unrecognized physical processes. The convergence of these improved observational and theoretical tools means that the coming years hold the prospect of significant advances in our understanding of WOHG64 and the class of extreme red supergiants it represents. We may soon know with much greater confidence whether it has a binary companion, what its precise radius and mass loss rate are, how it is evolving on timescales of years to decades, and what kind of final explosion it will produce. These answers will not only resolve outstanding questions about this particular star, but will also refine our models of massive stellar evolution more broadly, with implications for everything from the rate of supernova explosions in galaxies to the production rate of heavy elements and the formation of compact objects. There is something philosophically striking about the position of WOHG64 in our sky and in our understanding of the cosmos. It is invisible to the naked eye, hidden behind its own expelled material, detectable only with the most sensitive infrared instruments and the most sophisticated spectroscopic techniques. It lies in a galaxy that is itself barely visible to the naked eye as a faint cloud on a dark southern night. And yet, when we finally pierce through the dust and measure what is there, we find something that challenges the very equations we use to describe how stars work. The universe consistently reveals that the extremes are where the most interesting physics happens, where the rules bend, where new phenomena appear that were not anticipated by theories built on more ordinary cases. Black holes revealed that general relativity predicts singularities where the theory itself breaks down. Quantum mechanics revealed that at the scale of atoms, the familiar rules of classical physics give way to probabilities and uncertainties. And extreme stars like WOH-G64 reveal that even the physics of something as familiar as a star can be pushed into regimes where our best models struggle to keep up with what nature has actually produced. This is not cause for discouragement. It is cause for excitement. Every place where a model fails is an opportunity to learn something new. Every star that defies prediction is a clue about what physics is missing from our current picture. The history of science is full of examples where anomalies that seemed like problems turned out to be harbingers of major conceptual advances. The anomalous motion of Mercury's perihelion, which Newtonian gravity could not account for, pointed toward general relativity. The anomalous spectral lines of hydrogen, which classical physics could not explain, pointed toward quantum mechanics. The anomalous brightness of distant supernovae, which the expected matter-dominated cosmology could not accommodate, pointed toward dark energy and the accelerating expansion of the universe. H.G.64 may not harbor a discovery of that magnitude, but it is a real and significant anomaly. A star that exists where theory says it should not, behaving in ways that push the boundaries of our stellar evolution models. Understanding it completely will require better observations, better simulations, and possibly better theory. And when that understanding is achieved, it will be one more piece in the larger puzzle of how stars form, evolve, and die, how galaxies are chemically enriched across cosmic time, and how the universe created the conditions for the complexity we observe around us and within us. The light from WOH-G64 that we currently observe left that star before the invention of writing, before the construction of the first cities, before human civilization had begun to develop in any recognizable form. That light has traveled across more than 160,000 light-years of space to be collected by our telescopes and analyzed by our instruments. The information it carries tells us about a stellar object so extreme that it forces revisions to our best theoretical frameworks. The fact that we have developed the instruments and the mathematics to decode that information is itself a remarkable product of the evolutionary and cultural processes that have operated on our own small world over the same time period. We are, as a species, only recently capable of doing this kind of astronomy. The first generation of infrared telescopes sensitive enough to detect WOH-G64 and measure its properties became available in the latter half of the 20th century. The interferometric techniques that resolved its dust envelope required technology that matured in the 1990s and 2000s. The computational tools needed to model its spectral energy distribution and infer its physical parameters developed in parallel with the growth of modern computing infrastructure. We are at an early point in the history of this kind of investigation, and the tools available in the coming decades will be qualitatively superior to what we have today. This makes the present moment a genuinely exciting time to study objects like WOH-G64. We are moving from the era of detection and rough characterization into the era of detailed physical understanding. The James Webb Space Telescope is already producing observations that were impossible before its launch. The extremely large telescope, when it achieves first light later this decade, will resolve the circumstellar environments of nearby massive stars with a clarity that will transform our understanding of stellar mass loss and circumstellar chemistry. The Rubin Observatory will provide an unprecedented time-domain view of stellar variability throughout the Milky Way and the Magellanic Clouds. The next generation of gravitational wave detectors will be sensitive enough to detect stellar collapse events in nearby galaxies. Taken together, these new capabilities represent a step change in what we can learn about extreme stellar objects. The story of WHG 64 is therefore not a completed one. It is a story in progress, with the most informative chapters still to be written as new instruments and new techniques are brought to bear on its mysteries. The star itself continues its slow, violent dissolution, indifferent to our attempts to understand it, burning its final fuel and shedding its outer layers into the Large Magellanic Cloud. When it finally dies, whether that moment has already passed unbeknownst to us or still lies in the future, it will not be a quiet event. It will be a release of energy on a scale that dwarfs everything our civilization has ever experienced. And we will be watching, our instruments pointed at that small region of the southern sky, ready to decode whatever message the universe sends when another giant falls. Until that moment arrives, we continue to observe, to model, to question, and to learn. The biggest star ever found is not the biggest mystery it poses. That distinction belongs to the set of physical questions its existence raises. Questions about the upper limits of stellar structure, about the role of binary interactions in massive star evolution, about the mechanics of extreme mass loss, about the transition from a living star to a dead remnant. These are questions that sit at the frontier of astrophysics, and they are being actively pursued by researchers on multiple continents, using instruments on the ground and in space, with theoretical models running on some of the most powerful computational facilities available. In the end, the behemoth star is more than a record. It is a question the universe is asking us, a question about what is possible, about where the limits lie, about what we do not yet understand, and we are only beginning to formulate the answer. To fully appreciate the significance of WOHG 64 in the landscape of stellar astronomy, it is worth walking through in detail what we know about the life cycle of a star at this mass range, from birth through the various evolutionary stages to eventual death, because this entire journey is compressed into a timescale that is short even by stellar standards, and because each stage leaves observable traces that we can detect and study. The formation of a star with an initial mass of 20 to 40 solar masses begins in a molecular cloud, a region of interstellar space where gas and dust have been compressed to densities high enough for gravity to overcome the thermal and turbulent pressure that would otherwise prevent collapse. The triggering event for the collapse can be a nearby supernova shockwave, the passage of a spiral arm density wave, or simply the random fluctuations in the turbulent velocity field of the cloud. Once a sufficiently dense region begins to collapse, it heats up as gravitational potential energy is converted to thermal energy. The central region, called the protostar, becomes increasingly luminous as it accretes material from the surrounding envelope. For a massive protostar, the accretion phase is violent. The protostar begins fusing hydrogen in its core long before accretion has finished, and its luminosity quickly becomes comparable to the accretion luminosity. The radiation from the protostar ionizes the surrounding gas, creating what is called an Hg region, a bubble of hot ionized hydrogen that expands outward and can potentially halt further accretion. For the most massive stars, this feedback may be the ultimate limit on how massive a star can become. Accretion eventually stops either when the surrounding envelope is exhausted or when the radiation pressure becomes strong enough to reverse the infall. Once the young massive star has settled onto the main sequence, fusing hydrogen in its core in a stable configuration, it begins the process of gradually burning through its fuel. The core temperature and pressure are maintained by the balance between gravity and nuclear energy release. But the composition of the core gradually changes as hydrogen is converted to helium. When the hydrogen in the core is exhausted, the core begins to contract. This contraction heats the surrounding hydrogen-rich shell, which then begins to fuse hydrogen. The additional energy released from this shell burning causes the outer layers to expand dramatically, and the star begins its transition to the red supergiant phase. The details of how this transition occurs depend sensitively on the mass of the star, its initial rotation rate, its metallicity, and whether it has a binary companion. For isolated non-rotating stars in solar metallicity environments, the standard picture involves a relatively smooth transition to a red supergiant with increasing luminosity and decreasing surface temperature. For stars in low metallicity environments like the Large Magellanic Cloud, the reduced opacity of the stellar material means that the outer layers can expand more easily. potentially reaching larger radii before the star's internal structure becomes unstable. This may be one reason why some of the most extreme red supergiants are found in the Large Magellanic Cloud rather than in the Milky Way. Once in the red supergiant phase, the star begins fusing helium in its core. Helium fusion produces carbon and oxygen through the triple alpha process, in which 3 helium nuclei combine to form carbon-12, and subsequent alpha capture on carbon-12 produces oxygen-16. These reactions require higher temperatures than hydrogen fusion and are therefore more sensitive to the thermal state of the core. The helium burning phase lasts roughly 100,000 to 1 million years for a massive star, much shorter than the hydrogen burning main sequence phase. During the red supergiant phase, the luminosity of the star is high and the outer envelope is convectively unstable over a large fraction of its volume. Deep convective mixing carries processed material from the interior to the surface and fresh unprocessed material downward. This dredge-up process changes the surface composition of the star, bringing helium, carbon, and nitrogen to the surface in proportions that reveal something about the internal mixing that has occurred. Spectroscopic observations of the surface composition of red supergiants therefore provide indirect constraints on the internal physics of convection and mixing that would otherwise be inaccessible. For BOHG 64, the surface composition is partially obscured by the thick circumstellar dust envelope, but molecular spectroscopy of the inner wind material has revealed something about what the star is currently ejecting. The presence of oxygen-rich molecules like silicon monoxide and water vapor, rather than the carbon-rich molecules that would be expected if the surface were dominated by the products of helium burning, suggests that the star is still in a phase where oxygen is more abundant than carbon at its surface. This is consistent with a red supergiant that has experienced some convective dredge-up, but has not yet converted all of its surface oxygen into carbon through the further processing that would occur in a later evolutionary stage. The progression through successive nuclear burning stages after helium burning occurs in the stellar core at increasingly high temperatures and densities. Carbon burning ignites at temperatures of around 500 million to 1 billion Kelvin, producing neon, magnesium, sodium, and other intermediate mass elements through a variety of nuclear reactions. Neon burning occurs at temperatures above 1 billion Kelvin, producing oxygen and magnesium. Oxygen burning occurs at temperatures of 1 to 2 billion Kelvin, producing silicon, sulfur, and other elements. Each successive burning stage is shorter than the last because the nuclear reactions proceed faster at higher temperatures, and because the energy released per unit mass decreases as you move up the periodic table toward iron. Silicon burning is the final stage before collapse, and it is both spectacular and brief. At temperatures of several billion Kelvin, silicon nuclei are rapidly converted into iron peak elements through a complex network of reactions called nuclear statistical equilibrium, in which the abundances of different nuclei are determined by a balance between forward and reverse reaction rates rather than by the individual reaction cross-sections. The entire silicon burning phase lasts only a few days for a massive star. When it is finished, the core consists almost entirely of iron and nickel isotopes. The stage is set for the end. The iron core continues to grow in mass as silicon burning continues in a shell surrounding it. When the core mass reaches the Chandrasekhar limit, which for a core at these temperatures is roughly 1.3 to 1.5 solar masses, the thermal pressure from electron degeneracy can no longer support the core against gravity. The core begins to collapse. Within a fraction of a second, the density in the center of the core exceeds that of nuclear matter, about 2 times 10 to the 17th kilograms per cubic meter. At this point, the strong nuclear force, which is repulsive at very short range, begins to resist the compression and the collapse halts. The outer part of the infalling core smashes into this stiffened inner core and rebounds outward in a shock wave. This shock wave is the beginning of the supernova explosion, but it is not immediately powerful enough to blow up the star. As the shock wave propagates outward through the still infalling outer iron core, it loses energy by dissociating iron nuclei back into protons and neutrons, a process that absorbs energy rather than releasing it. The shock wave stalls, typically at a radius of a few hundred kilometers, creating a standing accretion shock. The revival of this stalled shock is one of the central unsolved problems in core collapse supernova theory. Current models involve a combination of neutrino heating, turbulent convection behind the shock, and hydrodynamic instabilities that together conspire to reinvigorate the shock after a delay of several hundred milliseconds. When the shock is revived, it propagates outward through the rest of the star, reaching the stellar surface several hours to a day later in a blast that is visible as the initial brightening of the supernova. For a star as massive and as extended as WOHG 64, the journey of the shockwave from the core to the stellar surface is a particularly long one. The star's enormous radius means that the shock must travel through several solar radii of material before it breaks out of the photosphere. This propagation time affects the timing and characteristics of the shock breakout emission, which is a brief but bright flash of ultraviolet and X-ray radiation produced when the shockwave reaches the stellar surface and heats the photosphere to millions of degrees. For a red supergiant with a large radius, the shock breakout occurs over a longer timescale and at lower temperature compared to a more compact blue supergiant, producing a different spectral signature that can in principle be used to constrain the progenitor's radius independently of other measurements. After shock breakout, the supernova enters the phase of photospheric expansion, during which the ejecta expands and cools while remaining opaque to optical and infrared radiation. The luminosity during this phase is powered partly by the diffusion of thermal energy deposited by the shock and partly by the radioactive decay of nickel-56 produced in the explosion. Nickel-56 decays to cobalt-56 with a half-life of about 6 days, and cobalt-56 decays to stable iron-56 with a half-life of about 77 days. The gamma rays from these decays deposit energy in the expanding ejecta, producing the characteristic light curve shape of a typical core collapse supernova, with a rise to maximum light followed by a decline whose rate is initially set by the nickel decay and later by the cobalt decay. For a star that has been shedding material as rapidly as WOHG 64, the interaction between the supernova ejecta and the circumstellar medium adds a significant additional component to the supernova light curve. The high-velocity ejecta, moving at several percent of the speed of light, sweeps up the surrounding circumstellar material in a powerful shock. This interaction converts kinetic energy to radiation, producing bright optical and radio emission that can persist for months or years after the initial explosion. If the circumstellar density is very high, as it would be for a star that has been shedding material at the rate observed for WOHG 64, the circumstellar interaction can dominate the total optical luminosity, making the supernova appear anomalously bright. Such superluminous supernovae have been observed in nearby galaxies and are thought to come precisely from the kind of massive, evolved stars that are still surrounded by dense circumstellar material at the time of their explosion. The remnant of the supernova will also be extraordinary. If a neutron star is formed, it will be spinning rapidly, perhaps hundreds of times per second, due to the conservation of angular momentum during the collapse of the stellar core. This rapidly spinning neutron star, called a pulsar, sweeps a beam of radio emission around like a cosmic lighthouse. If the beam intersects our line of sight, we detect regular pulses of radio emission with a period equal to the rotation period of the neutron star. Over time, the pulsar loses rotational energy to electromagnetic radiation and slows down, but the initial spin-down can power bright emission from the surrounding supernova remnant, creating what is called a pulsar wind nebula. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054, is one of the most famous examples, powered by a central pulsar that is still spinning 30 times per second more than 900 years after the explosion. If WOHG-64's collapse produces a black hole rather than a neutron star, the remnant will be very different. Black holes do not emit radio pulses or power pulsar wind nebulae through their spin-down. However, a black hole that is born with significant spin can power relativistic jets through the Blandford's-Najek mechanism, which extracts rotational energy from the black hole through magnetic fields threading the event horizon. If such jets are launched in the first seconds after collapse, they could produce a gamma-ray burst if they can punch through the stellar envelope. Even if no gamma-ray burst occurs, the jets could deposit energy in the surrounding circumstellar medium, potentially producing distinctive radio emission that could be detected years after the explosion as the jet decelerates and forms a hot cocoon of shocked material. The chemical legacy of the explosion will spread outward, into the Large Magellanic Cloud over timescales of tens of thousands of years. The shockwave from the supernova will first sweep up the circumstellar envelope that WOHG-64 has already built around itself, heating and compressing it before expanding further into the interstellar medium. As the shockwave decelerates, it will become Rayleigh-Taylor unstable, developing fingers and clumps as denser swept-up material decelerates slower than less dense material. These instabilities produce the complex filamentary structures seen in supernova remnants like the Cassiopeia A remnant, which is the debris of a massive star that exploded roughly 300 years ago. The composition of the filaments in Cassiopeia A reveals the products of nucleosynthesis in the progenitor star, with distinct regions rich in silicon, sulfur, argon, calcium, and iron from the innermost layers of the explosion. WOHG-64's remnant, observed from Earth, would provide an extraordinary opportunity to study these nucleosynthesis products in a system where the progenitor's properties are already well characterized. The combination of pre-explosion observations of the star, observations of the explosion itself, and subsequent monitoring of the remnant's evolution over decades and centuries would create an unparalleled data set for testing our models of massive stellar evolution. Nuclear physics and supernova dynamics. Each phase would answer questions raised by the previous ones and pose new questions for the next. It would be the most comprehensively observed death of a massive star in the history of astronomy. This is the kind of scientific return that makes the ongoing monitoring and characterization of extreme stars like WOHG-64 genuinely worthwhile. The investment of telescope time and computational resources in studying a single star may seem extravagant when compared against the enormous number of other astronomical objects demanding attention. But the potential payoff, in terms of fundamental advances in our understanding of stellar physics and chemical evolution, justifies this investment many times over. The universe is full of interesting objects, but very few of them challenge our best theories in quite such a direct and pressing way as WOHG-64. We are fortunate to live in an era when the tools for studying such objects are becoming powerful enough to provide real answers. We are fortunate to have inherited the intellectual legacy of generations of astronomers and physicists who built the theoretical framework that gives us questions worth asking. And we are fortunate in a deeper sense that the universe produced objects like this one at all, objects so extreme that they force us to confront the boundaries of what we understand and push us to go further. WOHG-64 is a star at the edge of the possible. It is burning matter into energy at a rate that will exhaust its fuel in a geologically brief time. It is shedding its outer layers at a rate that would empty entire stars into the surrounding medium over the course of a few million years. It is sitting at, or beyond theoretical boundaries that say it should not be stable in its current configuration, and yet it persists. For now, the universe does not grant permanence to things this extreme. Eventually, and perhaps soon by cosmic standards, the balance will shift and the outcome will be catastrophic and irreversible. When that day comes, the universe will be slightly changed. The Large Magellanic Cloud will be lit by the death of one of its most extraordinary inhabitants. The material that spent millions of years inside the star will be scattered across light years of space, eventually to be incorporated into new stars, new planets, and new chemical systems. The information carried by the light from that explosion will reach our telescopes and tell us things we could not have learned any other way. And the questions that WOHG-64 raises today will receive at least partial answers in the data that flows from its death. That is the nature of extreme stellar objects. They live violently, they die spectacularly, and in their death they reveal things about the universe that no other phenomenon can. Understanding them is not simply an academic exercise. It is part of the larger project of understanding where we came from, how the universe built the conditions for chemistry and biology, and what role the most massive stars played in shaping the cosmos we inhabit. WOHG-64 is the current champion of stellar extremes. Its story is still being written, and we have only just begun to read it. Consider for a moment what it would mean to actually stand on a world near WOHG-64 and observe it directly. Not from 160,000 light-years of safe distance, but from within the same stellar neighborhood, perhaps 500 light-years from the star. At that distance, the star would be the single most prominent object in any sky. a vast crimson sphere so large that even at this distance it would subtend a substantial angle in the sky, dwarfing our own sun's apparent disk by a factor that would render the comparison absurd. It would not look like a point of light. It would look like a wall of fire, a curved horizon of roiling red plasma stretching across the sky from one edge of the horizon to the other on a world with the right viewing. Geometry. The light from WOHG 64 would be the defining feature of any nearby solar system's environment. With 280,000 times the solar luminosity, even at 500 light-years of separation, the stellar irradiation on a rocky world would be substantial. The electromagnetic environment would be harsh, saturated with infrared radiation and laced with X-rays and ultraviolet photons from the star's hot outer atmosphere and from the shock waves propagating through its wind. Any planetary magnetic field would be under constant assault from the stellar wind, which at the star's enormous mass loss rate carries a particle flux far exceeding what our own solar wind delivers to Earth's magnetosphere. And yet there is something deeply compelling about imagining a civilization that evolved in the shadow of such a star. A culture shaped by the knowledge that its sun is not a stable eternal fixture but a dying giant, measurably losing mass, surrounded by its own discarded material, visibly unstable on timescales accessible to scientific observation. Such a culture would have to grapple from its earliest scientific history with the knowledge that its star is temporary, that the bright red presence dominating its sky is not eternal but passing. The study of stellar physics would not be an abstract academic exercise but a matter of civilizational relevance, since the death of WOHG 64 would be of immediate existential consequence to any world within a few dozen light-years. The radiation from a core collapse supernova at 500 light-years would be bright enough to rival the full moon in apparent luminosity for weeks after the explosion, visible in daylight, bright enough to cast shadows at night. But the electromagnetic radiation is only the most visible part of the danger. The neutrinos from the collapse would pass through the planet essentially unimpeded. The cosmic rays produced by the expanding shockwave would gradually increase in intensity over the following years and centuries as the blast wave expanded and accelerated particles to relativistic energies. If the collapse produced a gamma-ray burst aimed in the direction of the planet, the initial radiation dose could be lethal on a civilization-altering scale. This kind of scenario, a technologically developed civilization facing the impending or actual death of its star, has been a staple of speculative fiction for decades. But when grounded in the actual physics of a real object like WOHG 64, the details become both more precise and more sobering. The star's death is not a hypothetical future event in some distant galaxy. It is a physical certainty for a specific object whose current state we can observe and measure. The question of when it will happen is uncertain, but the question of whether it will happen is not. And the consequences for any proximate observers would be profound. From our safe vantage point, however, the death of WOHG 64 is an opportunity rather than a threat. It is an event we can prepare to observe, an experiment we cannot perform but that nature will perform for us, a brief window into processes that normally unfold over millions of years compressed into days and weeks of observable light. The preparation for this observation is already underway in the form of the monitoring programs and theoretical modeling described earlier. When the event occurs, whether in our lifetimes or in the distant future, the astronomical community will be ready in a way it has never been before, equipped with instruments and computational tools that will extract the maximum possible scientific value from what nature provides. The monitoring of WOHG 64 with existing facilities is ongoing. Long-term photometric monitoring programs in the infrared track the star's brightness variations over months and years, looking for patterns that might reveal its pulsation period or progressive changes in the dust envelope. Spectroscopic monitoring watches for changes in the velocities and abundances of molecules in the wind, which could indicate changes in the mass loss rate or chemical composition. Radio monitoring follows the silicon monoxide master emission, which traces the innermost regions of the outflow closest to the stellar surface. One of the most informative future observations would be a detection of the star's actual photospheric emission, the thermal radiation from the stellar surface itself, separated from the reprocessed emission of the surrounding dust. The dust envelope is opaque at most wavelengths. but there are spectral windows in the mid-infrared, particularly around 10 micrometers and around 20 micrometers, where the dust opacity is lower and the photospheric emission can potentially be detected. Observations at these wavelengths with instruments like the Mid-Infrared Instrument on the James Webb Space Telescope could potentially reveal the temperature and radius of the photosphere directly, providing much more robust constraints on the star's physical properties than the model-dependent estimates currently available. The spatial resolution available to the James Webb Space Telescope is also sufficient to potentially resolve the inner structure of the circumstellar envelope, mapping the distribution of temperature and dust density as a function of distance from the star. This would allow a much more detailed test of models of the outflow, including whether the toroidal structure inferred from ground-based interferometry is confirmed at higher spatial resolution, and whether there are any asymmetric features that might indicate the presence of a binary companion or strongly anisotropic mass. Lost to future facilities at even longer baselines than currently available will push this further. The next generation Very Large Array, a proposed successor to the existing Very Large Array radio telescope, would provide unprecedented sensitivity and resolution at radio wavelengths, allowing detailed mapping of the molecular outflow at scales comparable to the star's own radius. The Square Kilometre Array, currently under construction in South Africa and Australia, will provide similar capabilities at a different range of frequencies. Together with the extremely large telescope in the optical and infrared, these future facilities will transform our ability to study extreme massive stars in the Large Magellanic Cloud and throughout the local group of galaxies. The timeline for these new facilities varies. The extremely large telescope is expected to achieve first light in the late 2020s. The Square Kilometre Array is also expected to reach full operation during the same approximate period. The next generation Very Large Array has been recommended in the United States ASTRO 2030 Decadal Survey for Astrophysics and may be funded and built during the 1930s. Collectively, these represent a step change in our observational capabilities that will make the next decade one of the most productive in the history of stellar astronomy. For WOHG 64 specifically, the most transformative single observation would be a direct detection of the binary companion star, if one exists. Confirmation of a companion would immediately open a new chapter in understanding the star, providing constraints on the orbital parameters, the mass ratio, and the dynamical history of the system. It would also influence the predictions for the eventual fate of the system, since binary interactions can dramatically alter the pre-supernova evolutionary track, the angular momentum of the collapsing core, and the geometry and energetics of the eventual explosion. The combination of mass transfer, tidal synchronization, and potential common envelope evolution in a binary containing a red hypergiant is a scenario that is rich in interesting physics and largely unexplored by current theoretical models. The detection of a companion would require either very high angular resolution, imaging in the near-infrared to directly see the companion's light against the background of the circumstellar dust, or very precise radial velocity monitoring to detect the reflex motion of the primary star induced by the gravitational pull of the companion. The former approach is limited by the density of the dust envelope, which may be too thick to allow near-infrared photons from the companion to escape without being completely absorbed. The latter approach requires very high signal-to-noise spectroscopy of specific spectral features in the wind, and disentangling the orbital motion from the intrinsic variability of the red supergiant's wind is a significant technical challenge. Polarimetric observations offer another avenue. Light that has been scattered by dust in the circumstellar envelope carries a polarization signature that reflects the geometry of the scattering material. If the dust envelope has a strongly anisotropic structure, as suggested by the toroidal morphology inferred from interferometry, the polarization of the scattered light will reflect that geometry. Changes in the polarization with time could reveal the orbital motion of a companion if its gravitational influence is distorting the dust distribution periodically. Optical polarimetry of red supergiants has been used to constrain the geometry of their circumstellar environments in several cases, and WOHG 64 is a natural target for this technique once the necessary sensitivity and angular resolution can be achieved. In the meantime, theoretical work continues to develop more sophisticated models of binary massive star evolution. Massive star mass loss and core collapse supernova dynamics. The field of stellar evolution has benefited enormously from advances in computational power over the past 2 decades, with three-dimensional simulations of stellar, convection, and supernova dynamics, revealing details that were completely inaccessible to the one-dimensional models that dominated the field for most of the 20th century. These advances have also revealed the limitations of one-dimensional models in ways that motivate further investment in higher-dimensional computation. For the specific challenge of modeling WOH-G64, the relevant physics includes the three-dimensional structure of convection in a red supergiant envelope, which determines the pattern and rate of mass ejection from the stellar surface. It includes the radiation hydrodynamics of the dust-forming wind, which determines the opacity and geometry of the circumstellar envelope. It includes the tidal interactions between the red supergiant and any companion star, which affect the mass loss geometry and the evolutionary track of both stars. And it includes the dynamics of the eventual core collapse and explosion, which determine whether a neutron star or black hole forms and what kind of supernova is produced. Each of these components is itself a substantial computational challenge, and coupling them together in a single self-consistent simulation is a problem for future computing infrastructure. The growth of machine learning as a tool in astrophysics is beginning to provide new approaches to some of these challenges. Neural networks trained on suites of stellar evolution models can rapidly explore the parameter space of initial conditions and physical assumptions, identifying which combinations produce outcomes consistent with observed properties of specific stars. Applied to WOH-G64, such approaches could be used to constrain the star's initial mass, age, and mass loss history more tightly than is possible from simple comparison with individual theoretical tracks. They could also be used to predict the range of possible outcomes for the star's eventual fate, providing probabilistic forecasts that account for the uncertainty in the current physical parameters. The study of extreme stellar objects, like WOH-G64, is therefore a genuinely multidisciplinary endeavor, involving observational astronomy at every wavelength, theoretical stellar physics and hydrodynamics, nuclear physics, radiation transport, and increasingly, computational and data science methods. The breadth of skills required reflects the breadth of the physical processes involved. A single star can be a laboratory for testing theories spanning particle physics, fluid dynamics, radiation physics, and general relativity, all within the same object over the course of its lifetime. This breadth is one of the reasons why massive stellar astrophysics has remained such a vibrant and productive field. The fundamental questions: how do stars form? How do they evolve? How do they die? What do they leave behind? Have been studied for over a century, and they remain partially unanswered precisely because the relevant physics is complex, coupled and difficult to observe in its most important manifestations. Every advance in observational sensitivity or computational power reveals new details that must be explained and often reveals new puzzles in the process. The field has not and will not run out of important questions anytime soon. WOH-G64 exemplifies this. It is an object that we have known about for half a century, that has been the subject of targeted observational campaigns for several decades, and about which there are still fundamental unanswered questions. Is it truly a single star, or is it in a binary system? What is its exact current mass and mass loss rate? Is it at or beyond the Hayashi limit, and if so, how is it maintaining its current configuration? What will be the sequence of events that leads to its eventual death, and what kind of remnant will it leave? Each of these questions has implications not just for this star, but for our understanding of the entire class of extreme massive stars and their role in galactic evolution. The answers will come, as they have always come in science, through the combination of careful observation, rigorous theoretical analysis, and creative physical reasoning. They will require patience, since some of the most important observations will require instrumentation that does not yet exist and computational resources that are not yet available. They will require collaboration, since the breadth of relevant expertise exceeds what any single research group can provide. And they will require sustained commitment, since the timescales for resolution are measured in decades rather than years. But the payoff for that patience and commitment is genuine. Understanding WOH-G64 at the level of detail that current and future instruments promise is not merely an exercise in celestial statistics. It is a contribution to the foundational project of understanding how the universe built itself, from the simple hydrogen and helium of the Big Bang, through generations of massive stellar furnaces that produced and distributed chemical complexity, to the rich, multi-phase, chemically diverse universe we observe today. WOHG-64 is one of the most extreme participants in that process alive in the local universe at this moment. Studying it is studying one of the most powerful engines of cosmic chemical evolution in action, in real time, at a distance close enough to resolve its details and measure its properties. That is an extraordinary scientific privilege, and it is one that the community of stellar astronomers is working to fully exploit. The star will not wait forever. Its time is running out on scales that are long by human standards but brief on cosmic ones. The observations that will teach us the most about it need to be made while it is still alive and in this extreme phase of evolution. The urgency is real, and it is driving an increase in focused observational and theoretical effort on this and similar objects. In the history of science, there have been moments when a single object or phenomenon, studied with sufficient care and sophistication, revealed fundamental truths about the physical world. The planet Mercury's orbit revealed the curvature of space-time. The motion of distant galaxies revealed the expansion of the universe. The cosmic microwave background revealed the thermal history of the early universe. WOHG-64 and the class of extreme stellar objects it represents may not yield discoveries of quite that magnitude, but they will yield real and important advances in our understanding of stellar physics and galactic chemical evolution. And in the cumulative progress of science, even incremental advances, built patiently on top of each other, eventually add up to transformative understanding. We are building that understanding now, measurement by measurement, model by model, observation by observation. WOHG-64 is one of the most demanding and rewarding subjects for that endeavor. It is the largest star ever found, a star that challenges our theories, expands our imagination, and connects us, through the physical chemistry of the atoms we are made of, to the cosmic processes that made the universe what it is. It is worth studying with everything we have, and it is worth communicating clearly because the story of what the universe can do, told honestly and in full detail, is among the most astonishing stories there is. The relationship between our species and the stars is older than any written record. Before telescopes, before spectroscopy, before any understanding of nuclear physics or stellar evolution, humans looked at the night sky and recognized that what they were seeing was significant, that the patterns and motions of those points of light were connected to something real and important. The constellations they drew were not merely decorative. They were the first attempt to organize the sky into a comprehensible map to find structure in the apparent chaos of stellar distribution. Every culture in human history has looked up and tried to make sense of what is there. What we have learned in the past century and a half of modern astrophysics is that the stars are more extraordinary than any pre-scientific imagination could have conceived. They are not lights fixed to a crystalline sphere. They are nuclear furnaces, gravitationally compressed spheres of plasma in which atomic nuclei are smashed together at millions of degrees to release energy through mass-energy conversion. They are the chemical factories of the cosmos. They are the primary gravitational organizers of galactic structure. They are the producers of the electromagnetic radiation that makes the universe visible to us in the first place. And among all the stars that exist in the observable universe, numbering in the hundreds of billions, a small fraction are so extreme that they challenge the very theoretical frameworks we use to describe stellar behavior. WOHG-64 is one of these. It is extreme in size, with a radius that pushes up against and perhaps exceeds theoretical stability limits. It is extreme in mass loss rate, shedding material into its surroundings faster than almost any other red supergiant we have ever measured. It is extreme in its circumstellar environment, surrounded by a dust structure that extends to about 1 light-year, and that may contain several solar masses of expelled material. And it is extreme in what it tells us about the possible range of stellar behavior at the high-mass end of the main sequence. Understanding. The WOHG-64 is therefore not about satisfying curiosity about a distant curiosity, ways that are still poorly understood. The legacy of WOHG-64 will be measured in the distribution of heavy elements throughout the region of the Large Magellanic Cloud where it currently resides. When it dies, The supernova shockwave will sweep up the circumstellar envelope it has been building for millions of years and hurl it into the surrounding interstellar medium. The heavy elements produced in the star's interior will mix with the local gas, enriching it in carbon, oxygen, silicon, and elements produced only in the explosion itself, including iron group elements and possibly R-process elements produced by neutron capture during the collapse. This enriched gas will eventually be incorporated into new molecular clouds, new protostars, new planetary systems. The atoms will disperse and recombine in configurations we cannot predict. This is the cycle of stellar evolution writ large, the process by which galaxies become chemically richer over time. The process by which the universe moved from a state of almost pure hydrogen and helium to the chemically complex state required for the formation of rocky planets and biospheres. Every generation of massive stars contributes to this enrichment, and the most massive stars contribute the most per individual event. Would G64, when it dies, will contribute more heavy elements to its galactic environment in a single event than our entire Sun will produce over its entire 10 billion-year lifetime. That is the measure of what extreme stars mean to the cosmos. They are brief but powerful participants in the long process of cosmic chemical evolution. Studying them is studying the history of matter itself, tracing the path from the simplest atomic nuclei to the complexity that surrounds us and constitutes us. WOG64 is the current extreme, the largest and one of the most luminous red supergiants ever found, a dying giant in a neighboring galaxy, shedding itself into space and counting down toward an explosion that will briefly light up its corner of the universe. Its story is the universe's story, told in the language of nuclear fire and stellar wind and drifting dust. It is a story worth understanding in full. The stars we observe are snapshots. Light takes time to travel, and the further away a star is, the older the image we receive. When we look at WOG64, we are not seeing it as it is right now. We are seeing it as it was 163,000 years ago. The star we observe tonight might have already exploded. Its death might already be a historical fact. The supernova light already racing toward us across intergalactic space, arriving perhaps tomorrow, perhaps in 10,000 years, perhaps already streaking through the outer solar system at this moment. We have no way of knowing until the photons arrive. This delay is not an inconvenience. It is a feature of the universe that gives astronomy its strange temporal dimension. When we survey the sky, we are looking at a population of stars at different distances and therefore at different moments in time. A star 100 light-years away is seen as it was 100 years ago. A galaxy 1 billion light-years away is seen as it was 1 billion years ago, when the universe was younger, denser, and chemically different from today. This allows astronomers to study the evolution of stellar populations and galaxies by comparing objects at different distances, effectively looking backward in time. For WOG64, this temporal displacement adds an element of suspense that is entirely real. The star is in an unstable state that cannot persist indefinitely. Theory and observation both suggest it is approaching the end of its life. But when the end will come is uncertain, and the uncertainty is genuine because the physics governing the final stages of massive stellar evolution is not fully understood. The star could persist in its current state for tens of thousands of years, or it could collapse within the next millennium. There is no reliable way to predict the timing with the precision we would need to say which scenario applies. What we can do is keep watching, keep measuring, keep refining our understanding of what the star is currently doing and how that relates to its eventual fate. Every observation adds a data point. Every new measurement of the mass loss rate, the pulsation behavior, the dust distribution, or the spectroscopic signatures of the stellar wind constrains the models more tightly and brings us closer to a confident physical picture of the star's current state and near-future evolution. This is the patient, methodical work of observational science, and it is as essential as the more dramatic discoveries that occasionally punctuate it. The study of WOG64 is ultimately a study of limits. The limits of stellar size, the limits of stellar stability, the limits of our observational reach, the limits of our theoretical models. And in pushing against those limits, we learn something not just about this particular star, but about the physical principles that determine what is possible in the universe. Every time a star is found that challenges existing models, it is an invitation to improve those models, to include physics that was previously neglected, to test assumptions that were previously taken for granted. This is how science progresses, not by confirming what we already know, but by confronting what we do not. OHG64 has been confronting us since it was first identified as an unusual infrared source in the 1970s. In the decades since, each new observation has revealed additional layers of complexity, and each new model has had to be extended or revised to account for what the observations show. This process will continue as new facilities come online and new analytical techniques are applied. The star will eventually die, removing itself from our observational roster, but the data it provides while alive and the data from the explosion itself when it comes will continue to be scientifically productive for decades after the event. In this sense, WOHG64 is not just a star. It is a long-running experiment in stellar physics, one that has been collecting data for 50 years and will continue to collect it until the explosion ends the experiment with a burst of energy and information unlike anything that has been available before. The scientists who have devoted careers to studying this object, and those who will continue the work in the coming decades, are participants in an investigation whose conclusion will be among the most scientifically informative events in the modern history of astronomy. That is a remarkable thing to be part of. And for those of us who are not professional astronomers but who look up at the sky with curiosity and wonder, knowing that objects like WHG64 exist, that the universe contains stellar objects so extreme they challenge our best theories, is itself a source of genuine intellectual excitement. The cosmos is not a place of simple repetition and quiet stability. It is a place of extraordinary range and dynamism, where the most basic physical processes, gravity, nuclear fusion, radiation pressure, operate at scales and intensities that produce behavior we are still working to understand. WOHG64 is one of the most dramatic demonstrations of that fact currently accessible to our instruments, and its story is still unfolding.